of the power logic. It has been a while since last time we have recorded 2029 AMC8 solutions, and instead of actually doing some more competition math stuff, I would like to actually start like some kind of technical teaches. And today we're gonna start with some basic proof ideas. So first we're gonna start with induction. So what is induction? Well, induction is a proof technique that normally deals with all natural numbers or all non-negative integers. So, for example, 0, 1, 2, dot, 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 and all the way to infinity, right? So basically, how does this work? The mechanism is that first we prove the base case, and then we show that whenever the statement holds for n, then it holds for n plus 1. So this is basically the mechanism of induction. So now you might get like, why does that only hold for non-negative integers or positive integers? Because if you do some kind of things with fractions or even square roots, then you can't really show n plus 1. And since since induction is kind of proving something that's discrete, not continuous, so we can't really, so it's only going to be viable for integers. So this basically, think of this as a domino, like the domino blocks. So first you push the first one, and then whenever n falls, whenever the nth block falls, then it's gonna push down to cause the n plus 1 block fall. So therefore, this is gonna be a really powerful proof technique that you're gonna see a lot in stuff that's related to discrete math, or even sometimes, well, in number theory. So let's get started. So now let's think of a or like, I'm gonna present a really simple example. So for example, we're gonna show that 1 plus dot dot 1 plus 3 plus dot dot plus 2n plus 1 is equal to n squared. You might heard of this, you might not, but this is actually a well-known, which is the sum of the first n positive, the sum of the first n yeah, the sum of first I think, well, actually it should be like this: the sum of the first n minus 1, or the sum of the first n I would say the first n odd positive integers is equal to n squared. So how do you prove this? Well, actually, pause this video and try to think of whether you can prove this by just using simple arithmetic series summation. Well, actually, it's probably possible, right? You can just say that, well, this first term plus last term times the number of terms divided by 2. But that might be a little bit tough for the next example that I'm going to present. But for this one, you can do that. But let's just stick with induction. So first, what's the base case? Well, the base case is that, well, what if when n is equal to 1, then 1 is equal to 1. So that's definitely true, no big deal. And what next? What's the next? Well, remember, our inductive hypothesis is that 1 plus 3 plus dot dot plus 2n minus 1 is equal to n squared. So we're gonna show that if n works, then n plus 1 works. So what does it mean when n works? Then basically this works, right? So n works, then 1 plus inductive step, or 1 plus 3 plus dot dot plus 2n minus 1 is equal to n squared. This works. Then we have to know that 1 plus 3 plus dot dot plus 2n minus 1 plus 2n n plus 1 minus 1 is equal to what? It's equal to n squared plus 2 times n plus 1 minus 1. right? Because we already assume that 1 plus 3 plus dot dot plus 2n minus 1, so the first n odd integers is equal to n squared. Then we can just substitute, right? We just substitute this as n squared to see what's going to happen. And then we get this expression, which is n squared plus 2 times n plus 1 minus 1. And just do some kind of simplification, you're going to get n squared plus 2n plus 1. And aha, this is exactly n plus 1 squared, right? Which is equal to n plus 1 squared. Thus, we just showed that whenever n works, then n plus 1 is going to be extended from the result of n squared. So therefore, we have proved this claim, QED. Now, you might say, well, what's the specialty of induction? You can just do the sum of the first element plus the last element times the number of elements divided by 2. And what's the special of induction? Well, what if we look at another example, which is the sum of the squares of the first n integers? Well, actually, the sum of the cubes of the first n integers. 1 cube plus 2 cube plus dot 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 plus n cube. What's that going to be? And that, in fact, is going to be equal to 1/4 times n plus 1. Well, actually, n squared times n plus 1 squared. So now, can you still do sum of the first element plus the last element? Well, no, because the difference between two cubes are not constant, so it's not an arithmetic series, nor is it a geometric series. So how are we going to prove this? And notice that this one basically just means what? Basically means the square of n times n plus 1 over 2. And what is that? Well, that is exactly the sum of the arithmetic series that ranges from 1 to n that actually steps by 1. So now this is actually a perfect time to do induction because you don't really see any way out and you can't really force to find the sum explicitly. So now let's still stay with our base case. Well, base case is trivial, just plug in 1. Well, 1 cube is equal to 1/4 times 1 square times 2 square, which is equal to 1. So square, which is the subclaim being proved. Now what about the inductive step? Well, inductive step now basically just becomes that, we didn't know that 1 cube plus 2 cube plus dot 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 plus n cube, the sum of the first n cubes is equal to the square of the sum of the first n terms, right? So actually, let me just write it in a bit clearer way. N squared plus n squared. Which leads to 1 cube plus dot 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 plus n cube plus n plus 1 cube. That is equal to 1/4 times n squared plus n squared plus n plus 1 cube. So now what is that equivalent to? Let me just make it a bit bigger to make it clearer to look. Now from here, well, we just want to simplify this, right? And notice that we can take out an n plus 1, a factor of n plus 1 for both of these expressions. So we can just take out a n plus 1 times, the left term becomes 1/4 Well, actually, we can even take out a 1/4. So just to simplify the calculation, no big deal. And 1/4 times n plus 1 times, well, here is going to be, well, actually we can even just take out the n plus 1 square. That's going to be even simpler. And n plus 1 square times, well, the left hand side becomes n squared. And plus, well, keep in mind that we have to still multiply by 4, so n squared plus 4 times n plus 1. And now we can just simplify this part, the part in the large parentheses. That simplifies to 1/4 times n plus 1 times n squared plus 4n plus 4, which is equal to 1/4 times, well, it's n plus 1 squared, excuse me, times n plus 1 squared times n plus 2 squared. Which is indeed just 1/4 times n plus 1 squared times n plus 1 plus 1 squared. And this basically ends our proof. So now I hope that after these two examples, you have already seen or visualized the powerfulness of induction. And now let's actually do a more, I would say, fun puzzle, because you probably don't want to deal too much about these numbers. So now let's talk something about Hanoi towers. Well, it's actually a pretty famous puzzle, and if you do not know that, then I'm gonna shortly discover it, or shortly describe it. So first, Hanoi tower basically means that I have 3 towers, right? 3 towers, but 2 of the towers are empty. So I have 3 towers with 2 of them empty and 1 of them stacked with n coins with radius 1, 2, all the way to n. So now I have these 3 towers, and I can move any coin to any different tower at each second, 1 at a time. By following the following rules. So what are the rules? So first, so the first rule is that no coin can be stacked on a smaller coin. So basically, it just means that coins must be sorted in the range from the least to the greatest, from the top to the bottom. And second is that we cannot move the 2 coins at the same time. And this actually well, it's basically saying that 1 at a time. So, but I'm just gonna clarify: no 2 coins can be moved at the same time. Okay, cool. But what are we going to do? So what are we gonna do about it, and how is that gonna be related with induction? Well, pause this video and give a try on that, and just play around with this to see like a strategy to play this game when n is like bigger, and maybe try to explore what kind of n would actually make this to be possible. So basically, we want to move this coin so that we want to completely move the tower to another tower in the same order, but not the same tower. So how are we gonna do that? Well, now let's think, right? When n is equal to 1, then what do you do? You just move it to another place, right? Simple. And what about n is equal to 2? Well, basically means that you have 1, 2, something like 1, 2, 0, 0. So this is when this is when the case when n is equal to 2. Now you want to move 1 first, right? So you want to move 1 into some other places. So now you have 2 left. Well, you have only the coin was radius 2 left in the original tower, and you move 1 to another tower. And 0 just means that you have empty. So now I moved it further. I'm gonna get then you want to move 2 into another tower, right? The third tower that's different from 1. So you get 0, 1, 2, right? And now we just want to move 1 onto the top of 2. So one more step and we get 0, 0, 1, 2. Pretty simple. But now, what if n is equal to, like, let's say 10, 20, 40, 80? Then how can we simulate? And without even simulating that, then how do we even know if we can possibly have a construction that would move the coins successfully? Well, this is actually the power of induction. Well, when we hypothesize that it works for all positive integers n, then if we can find a recursive relation between n and n plus 1, then we can easily just show that then we can just easily show that it's gonna work for all positive integers, and in fact we can even derive a formula of how many steps we need to take for it to be successfully moved to another tower by using induction. So let's do that. So first, assume that n work. Also, first 1 definitely works, and assume that n works, right? So n works. We're starting at 1 dot 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 n comma 0 comma 0. Right, these are the 3 towers. Now the recursive relation just comes from, well, we just stack. We just stack an n plus 1 below n. So then the problem of n plus 1 is simply just 1 dot 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 and n plus 1. Right? So now I still encourage you guys to just pause this video and think whether you can find some discoveries before I reveal the actual answers. Yeah, okay, so now let's continue. So the problem of the n plus 1 is this. And what do we do now? Well, let's just ignore n plus 1 for now, right? It's kind of just misleading, but we only care about 1 comma n, 1 all the way to n. And n plus 1 is not going to affect our decision of about 1 dot 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 n. So basically, the way we're going to stack those coins is going to be independent from the n plus 1 coin. So basically, we have to first move the stack of 1 to n to another tower. And that is basically the problem that we want to solve with the with the n case, right? Then after that, also basically we just successfully move this into 0, 1, and well, actually n plus 1. So basically we just leave n plus 1 coin, while the coin was with radius n plus 1, at the original position, and we move the entire tower from 1 to n to, well, to another different tower. And then from here, we just move n plus 1 to this empty tower, right? Since we have 3 towers, and then we already occupy 2 of the towers, so we move the n plus 1 coin to the last tower. So this becomes 0, 1, n plus 1. And now the problem becomes the same. We want to move this tower to this, which is the same as moving a tower from its original position to a different position. So then we can just successfully do it with 0, 0, and n plus 1, right? And we're basically done. So we have just successfully proved that it's gonna be possible for every positive integer. And we just want to show that 1, well, the base case, which is that when n is equal to 1, we can move. And that's pretty clear, right? We just move the only coin to another tower, and we're done. One move. So now let's do an extension problem. Can you find the number of steps we need to take to move the n tower? Now pause the video again and try to find the answer or make some kind of discovery on your own. And keep watching if you want to continue to look at the full solution. But we can just kind of get some kind of intuition from this true and false, or the Boolean statement that we just got, which is and always work. And now let's just take a look at the steps that we need to take to transform from the n problem to solve of n plus 1 problem. So first, we want to move 1 comma comma n, which is the n tower, to another tower, right? Which is, well, we need a sub n. So a sub n, so a sub n is basically just the number of steps to move the n tower to another place. So a sub n plus 1 is gonna be equal to a sub n. Now we want to move n plus 1 to another place, right? From the first position to the third position, and that needs 1 step. And then we want to move this n tower to the tower that n plus 1 is currently at. So another a sub n. So which is 2 a sub n plus 1. So basically our recursion is basically just a sub n plus 1 is equal to 2 times a sub n plus 1. And we have a sub 1 is equal to 1. Yeah, okay, we have the recursion and we have the base case. Now is the time to do induction. So first, now let's take a look at, well, what is a sub 2? Well, a sub 2 is equal to 2 times 1 plus 1, which is 3. And what about a sub 3? Well, a sub 3 is equal to 2 times 3 plus 1, which is 7. And what about a sub 4? Well, a sub 4 is equal to 2 times 7 plus 1, which is 15. Now, do you see any similarities? Well, yes, because these are basically just one off from a perfect square, and that's really, really helpful because we can just make a hypothesis that or a sub n is equal to 2 to the n minus 1, right? So that's our inductive hypothesis. So now how do we continue? Well, we just say this to be a hypothesis, and clearly the base case works, right? A sub 1 is equal to 2 to the 1 minus 1, which is 1. So now, well, a sub n is equal to 2 to the n minus 1, then a sub n plus 1 is equal to 2 times 2 to the n minus 1 to a sub n plus 1, which is 2 times 2 to the n minus 1 plus 1, which is 2 to the n plus 1 minus 1. And we're basically done with this problem. So I hope that after this video, you can get a sense of the power of proof techniques, and also how induction is pretty powerful to solve problems that we cannot really solve with our ordinary techniques. So thank you for watching, peace out, and I'll catch you in the next video. Goodbye.